Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Greene, who is a professor of astrophysics at Princeton University. Her broad research interests include measurements of black hole masses, the connection between supermassive black holes and galaxies, stellar and gas kinematics of galactic nuclei, and diffused light in galaxy clusters. She also serves on the leadership committee of the Prison Teaching Initiative at Princeton University. Welcome, Jenny.
Thank you.
I want to start with something very topical, and that's the Nobel Prize for Physics this year that was shared by Roger Penrose, Reinhard Genzel, and Andrea Ghez. And they have all worked in this area of black holes, and that is your research area as well. I wondered if you could briefly talk about their contributions to this area.
Yeah, I think I can focus mostly on the work of Andrea Ghez and Reinhard Genzel, their groups, and they have really been zooming into the very center of our own galaxy, the Milky Way, and painstakingly over decades, taking pictures of stars right at the center of our galaxy, and then piecing together the orbits of those stars and finding that they move much faster than they possibly could if there was not a dark mass sitting right very much exactly at the center of our galaxy.
And so these are measurements taken over a long period of time. I've heard a little bit of what Andrea had talked about this. And she has taken these measurements from Hawaii, if I understand it correctly?
That's right, the Keck telescope.
Okay. So over what time period is?
Oh, man,
like 10, 15 years, I think, right?
I think it's more than that.
More than that. And so this is basically looking at an area that we sort of think there is a supermassive black hole, and we'll get into that with your paper. Something really unusual there at the center of the Milky Way galaxy. And she has been looking at that area and plotting how the stars move around that area, right?
Exactly. It's remarkable work because between us, I don't know if you've ever looked at a picture of the center of our galaxy, but we live in the disk of our galaxy. So between us and the galaxy center, I like to tell people it's a technical term. There's a lot of schmutz. There's a ton of gas and dust.
Right.
And so they've had to work in the infrared rather than the optical. So optical is wavelengths that are like our eyes can see. Infrared photons actually pass through the gas and dust, so allow us to peer through all of that stuff. But there are many additional technical challenges to working in the infrared. And Andrea and Reinhardt's teams were really at the forefront, always pushing the technology in order to observe these stars and their orbits. In addition, from year to year, they would have to figure out which star was which. So if you hear Andrea talking about this process, it's just remarkable because to reconstruct these orbits, they had to do all this crazy pattern matching. Now they've got full orbits for a couple of the stars, and it's a little bit easier. But back in the day when they started, it was just incredibly forward thinking to believe that after a bunch of epochs, a bunch of years of doing this, they were going to constrain the mass of the black hole, which now they've done with remarkable precision.
Yeah, so I guess from the velocity of the stars moving around that area, we can back compute what the mass might be of the black hole, right?
That's right, and how small the radius is, right? So what the signature of the black hole is the combination of the mass and the size. It's so dense, so much mass in such a small space.
Yeah,
that the only really plausible explanation is a black hole.
Yeah, so let's set the context. So a black hole, the little I understand about it, Jenny, is that it is a large amount of mass that is concentrated in a very small area, and that means that the gravity is so enormous in that small area that not even light can escape from it. And so we can't really observe a black hole. We can only see the effects of it, right? And so when was this first hypothesized? I know that theoretically this came out of the general theory of relativity, right?
That's right. So usually when I'm talking to audiences, I talk about Newtonian gravity, where there is a force of mutual attraction. But what general relativity really taught us is that there is curvature in space around massive objects, right? And so the reason this is important is that in Newton's gravity, light, which has no mass, would not know about gravity. But in general relativity, because light is traveling through space, it will also be deflected around massive objects. And this we see, this gravitational lensing is one example. And so you can then imagine if light can be deflected in traveling through space by massive objects, you could imagine an object that has so much mass in such a small space that not even light could escape its gravitational pull. And we know that in the universe, nothing travels faster than the speed of light. Right. And that's where this concept of a black hole came from. So we like to think about an escape velocity. That's how fast you have to move to escape the gravitational pull of an object. For the sun, it would be 620 kilometers per second. And then if you just imagine taking the mass of the sun and shrinking it down, if you made the mass of the sun fit into basically the size of Manhattan, 3 kilometers, then the escape velocity would be the speed of light. So then you would have a black hole.
Right. Yeah. So before we get into to one of your papers, formation of supermassive black holes, could you talk a little bit about sort of the demographics of black holes? I know that there are different kinds. Mm-hmm. Could you talk a bit about that?
Yes. So in fact, the first observational evidence that there were astrophysical black holes in the universe did come from what astronomers call stellar mass black holes. And these are black holes that are something like 10 times the mass of the sun or more massive. And they come about during the death of massive stars. So they can be an end product of the death of massive stars. And
it is only 1 to 10 solar masses, because when stars die, they're basically ejecting a lot of the mass, right? So this is what is left behind.
Right. And those late stages of stellar evolution, how much mass is lost versus retained to make either a neutron star or a black hole do vary from star to star, and whether or not you have a companion and things like that, how much metals you have in your atmosphere, things like that.
Okay. So 1 to 10 solar masses.
No, I don't think they ever get as small as 1.
Oh, okay. So at least 10.
10 is typical.
Okay.
But as we've now recently learned from LIGO, they extend much higher. So we had no observational evidence for stellar mass black holes above 15 or 30 or something like that. And now LIGO is routinely finding things, in fact, all the way up above 100 solar masses, which is something else we can talk about.
Yeah. So the LIGO experiment looking for gravitational waves, what they found, I thought initially was sort of two neutron stars merging, right?
Most of the LIGO events have been black hole mergers.
Oh, okay. Was the very first one neutron stars, though?
No.
Okay.
No, for sure it was two black holes, and they were 30-something solar masses each.
Okay. Yeah, so they're now routinely finding them, these mergers?
In fact, yes. And I think we certainly didn't expect to see so many black holes in that mass range. So just to back up briefly, before LIGO, the way we knew about stellar mass black holes is when they happen to have a companion star. And why is that important? Well, as you said, we can't directly observe a black hole because light can't escape its gravitational pull. So how can you observationally determine that there's a black hole? Well, this is where having a friend is helpful. And so what happens is, and this is what actually I studied as an undergraduate, if you imagine you have a star in orbit around a black hole, then what can happen is that occasionally material can be transferred from the star to the black hole. And when that happens, the gas that flows from the star to the black hole, it can't just fall into the black hole. It needs to get rid of energy and angular momentum. And in nature, the way that gas does that is through what we call an accretion disk. And then this accretion disk basically heats up and transfers the energy and angular momentum that the gas has outward and allows the gas to flow into the black hole. And then that accretion disk of gas lights up. So we can see these periodic bursts of emission from what we call X-ray binaries, because they emit in the X-rays, which are just basically a pair of a black hole and a star. Once that accretion stops, then we can look at how quickly the star is orbiting the black hole, and we can get a mass for the black hole. And that was the first line of evidence that there are astrophysical black holes.
Okay. I know that, and I don't know the details of that. Was there an attempt to actually take a picture of a black hole?
Well, I think you're thinking about the Event Horizon Telescope.
The Event Horizon Telescope.
That's right. Yeah. So this is another, I mean, it's just been such an amazing time to be in black hole research right now, between the Nobel Prize and gravitational waves finally being detected and the Event Horizon Telescope. So yes, they are seeing the black hole shadow. So they're seeing very close to the event horizon of the black hole in the galaxy M87, which is one of the biggest black holes in our relatively nearby vicinity. So just for some scale, we were talking about 10 solar mass black holes to 100 solar mass black holes, these stellar mass black holes. The center of our galaxy is 4 million suns. M87 is 1 billion suns.
Okay. Yeah, so those are what you call supermassive. Right. Okay. Now, what is counterintuitive without deep understanding of this is that these are really complex things, at least on the surface, but they can be defined by 3 simple parameters: mass, spin, and charge, right? So in some sense, they're the simplest of objects in the universe. Is that right?
It's certainly true that astrophysical black holes are described by actually just 2 numbers. They don't actually carry charge in the real universe, we don't think. So just mass and spin. That is true. Whether they are simple or complicated, I guess, depends on your point of view. Most of the work that I do is not related directly to the sort of general relativistic effects, but rather when you're far from the black hole, how you can measure that the black hole is there. And those dynamics are basically Newtonian, the motions of stars around black holes. And so it's, in terms of writing down the math, it's not so complicated.
Right. Yeah. So the three sort of generations in terms of size, solar size, supermassive, and anything in between, you call it intermediate size black holes. But I also understand that there were some hypotheses around primordial black holes, even really, really small, like the diameter of an atom or something like that.
Yeah, to my knowledge, there is as yet no concrete way to test for those. I think they would
Yeah.
potentially, if we understand the very early universe and the physics there better, and maybe if we detect gravitational waves from the early universe, then maybe we'll start to get some constraints on whether there are primordial black holes. But as an observer, I haven't paid terribly much attention yet because there isn't a way to observe them yet.
Okay, yeah, there was some interest in it because some speculate that that could be the kind of the missing dark matter, but there is no progress in that direction, I think, right?
I certainly we have not detected dark matter yet.
Right.
Whenever anyone
Okay.
asks me what's the one thing I want in my lifetime to see, that's the answer.
Right. And so there are different mechanisms by which these black holes form. Could you talk a bit about the different mechanisms? And you have done a lot of research in this area. So, what are the different ways they could form?
Well, so again, the stellar mass black holes, we think we know how they form, which is from the death of
Yeah.
massive stars. But the supermassive ones, we really just don't know. And just for a little bit more context as to why astronomers care about this, and actually tying back to this question of the Nobel Prize, when Andrea and Reinhardt started looking at the galactic center, monitoring the
Yeah.
stars in the galactic center, at that time, we did not yet know whether most galaxies had black holes at their center, supermassive black holes, or whether it was a really rare phenomenon. So this was another way in which they were very brave because it wasn't clear they were going to find something. There were
Right.
some
Yeah.
hints, there were some gas measurements that suggested that there was a black hole at the center. But
Mm.
I think Reinhardt was involved in. But in any case, it was a gutsy observation to undertake at that time. Since then, and in part motivated by their work, there have been a lot. There are about 100 what we call dynamical measurements of black holes, and that's basically where you use motions of stars or gas at the centers of nearby galaxies to say
Yeah.
these stars are moving too fast unless there's a black
Mm.
hole there. So they must be under the gravitational influence of a black hole. There's about 100
Right.
now. And that sample really allows us to understand that black holes are a ubiquitous component, at least of massive galaxy evolution. So most big galaxies, our Milky Way included, have supermassive black holes at their center. And so astronomers are really motivated to understand, when did that black hole grow? Which came first, the black hole or the galaxy? And then, of course, how important was that black hole in the life cycle of the galaxy? And just for context, black holes are something like 1,000th of the mass of the galaxy. So they are not a dominant component by any means, but they can, because they're so compact, there's just a lot of energy that goes into making that black hole, and a small fraction of that energy can do a lot of damage to the galaxy on large scale. So we're really motivated to understand when and how black holes formed. So now I'll get to your seeding question if you want, or did you want to ask another one?
No, I was just going to ask. So there are also some robust relationships observed between sort of the galaxy's parameters and the black hole itself.
That's right.
Right.
That's right. So in addition to
Yeah.
to coming to understand that most, if not all, massive galaxies host black holes, we also learned that indeed, if you tell me the mass of the galaxy, I can tell you the mass of the black hole to make a pretty reasonable guess within a factor of a few. And so some process is regulating the growth of those two components to keep them growing in lockstep over time.
Right. And so are we are we almost sure that you need a supermassive black hole to actually create a reasonable sized galaxy?
It's probably actually the reverse. You probably need the
The
black
reverse.
hole to keep the galaxy from getting too big. So when I was just starting graduate school, cosmologists, people who study the overall evolution of the universe from the beginning to now, they were having this major challenge that when they made universes in boxes and they just evolved galaxies forward in time, all the galaxies were too big and they were forming way too many stars at late times, just a few billion years ago. They were still making more stars than we see in galaxies today. And that's where we think the black hole is really important, because the black hole can heat gas and keep stars from forming at late times. So it's more it's more that you need the black hole to keep the galaxy from running away.
So it's more like a stabilizer. So you need perhaps a supermassive black hole to keep a galaxy at some level for a long period of time.
That's how we think about it. Yeah.
Okay. And so how do we think these supermassive black holes were formed?
And so there are basically three main channels that people think about, and I'll start with the one we've already discussed, which is making black holes with the death of massive stars. This is something that we know happens, at least in the present day universe, and at very early times, when the universe was young, 100 million years after the Big Bang, there would most of the gas, basically all the gas, would have been hydrogen and helium. No other what we call heavier metals or other elements. And that would mean that that very first generation of stars would very likely form pretty massive, because what those other metals do is it allows the gas to cool, which allows the basic unit of the star to form at a lower mass. Whereas if you can't cool, you end up building up a bunch more mass before you can have fusion in your core. And so we think that these very first stars could have made the first seeds of supermassive black holes. They might have made 100 sun black holes. That's the premise. That would, for that channel. And I like this channel because we know it happens. We know that the death of massive stars can make black holes. The challenge and the reason people came up with other possible channels is that we see billion sun black holes only a couple million years after the Big Bang.
Oh wow! Okay, so are those what we call the quasars, or no?
Those are the very first quasars. Yeah, and it's pretty hard, if not impossible, depending on what you assume, to grow from 100 suns to over 1 billion suns in such a short period of time. You basically have to grow the black hole continuously and force feed it at higher rates than we think is necessarily physical for that entire time. And so this has been a tension for a very long time, since we found these first early quasars, and led people to try to come up with a way that you could make seed black holes heavier. So instead of making them at 100 suns, try to make them 1,000 or 10,000 or 100,000. And so there's a sort of general class of models that people call, quote, direct collapse models, where instead of actually forming a star and allowing it to burn through its hydrogen and go through its stellar evolution, you basically form the black hole kind of directly.
So there's a lot of hydrogen and helium around. Just gravity keep accumulating them, and at some threshold level, it just collapses even before it can actually become a star.
And exactly how that works, I don't think anyone totally agrees on. It may pass through what people call a quasi-star phase, where it is spherical and it's still accreting. And the challenge of this is that you basically need to really have the gas be just right. It has to not be too hot and not be too cold, because you don't want it to fragment into smaller stars. You need it to just all go into the black hole. If it has too much energy and angular momentum, it won't go into the black hole. And so the conditions for this direct collapse to happen are, depending on who you ask, either rare or impossibly rare. And so it's possible that there are enough of these direct collapse black holes that they can be the seeds of the very first quasars. In my reading of the literature to date, it seems unlikely that direct collapse black holes form the bulk of supermassive black holes today. Now, people still fight about this, but as I said, getting those conditions just right seems very challenging.
Okay. So then what is left is really sort of merging different black holes together to get to a big quasar.
So the third channel is merging, but in a very special environment. So again, the challenge of having the seeds be these 100 solar mass seeds that you make when stars die is A, that you can't make the first quasars, but B, also, if you're only 100 solar masses, you may never find your way to the center of the galaxy. You may never have enough gas around to grow. You mentioned merging with other black holes. If you're just out there in the middle of the galaxy, you may not find another black hole to merge with. So this third channel tries to solve that challenge by basically making the black hole in the center of a very dense cluster of stars. We see star clusters like this. They're called globular clusters today. They're some of the highest density of stars in the universe today. And you can imagine that at the centers of those clusters, you maybe could start with a few hundred solar mass black hole and have it grow through merging either of a bunch of massive stars early in the life of the cluster, or eating lots of black holes over a longer period in the life of the cluster. And both of those sort of sub-channels have been discussed in the literature. Either it happens quite quickly through mergers of stars, or it happens more slowly through mergers of black holes.
So these globular clusters, are they in a galaxy, or is this a part of a
Today,
galaxy?
they are almost all in galaxies, at least the ones that we know about. But we don't really know how globular clusters form. So it's kind of like kicking the problem, kicking the can down the road.
And so the hypothesis is that, if I understand this correctly, Jenny, is that it's sort of it's like a nursery for black holes. They get together, they get bigger, and when it gets to some size, they sort of gravitate toward the center of the galaxy. Is that the idea?
Right, that's right. So once you form the black hole in the globular cluster, then that cluster will find its way to the center of the galaxy. Exactly.
Okay. So during that trip, obviously, it has lot of raw materials to eat as well. And so, is there some sort of a mathematical process of, getting something made at some part of the galaxy, and that the migration process to the center that has been defined? Or
that part's pretty well understood. There's a process that's called dynamical friction. Basically the idea is that if you're a black hole star cluster combination, you're pretty dense, and you're moving through a field of stars. you're basically going to get a drag force on you from the gravity of all of those stars, and that will slowly cause you to lose energy in your orbit and head to the center of the galaxy. And if you're a intermediate mass black hole, because you're so dense, that process doesn't need to take forever. You could get there before the age of the universe. You not necessarily all of them, but it's possible for some of those globulars to get to the center. And in fact, there are special clusters that live at the centers of galaxies that are called nuclear star clusters, that people think potentially formed from the mergers of a couple of globular clusters that made their way to galaxy centers.
Okay. Do we know what the role, if at all, anything that dark matter is playing in this process?
No, the concrete answer is no, but the best guess is not much of a role, and the reason is that the fraction of mass at the centers of galaxies that comes from dark matter is quite low, because gas, which is what galaxies start out as, has ways of getting rid of its energy by interacting with other gas particles. So stars and gas and dust tend to be more concentrated to the centers of their dark matter halos, whereas the dark matter itself can't, except by being dragged along by the regular matter. And so the dark matter halo is really extended, and the galaxy, the part we see, the stars and the gas and the dust, are all much more concentrated. So it's pretty likely that all these black hole processes are almost completely dominated by regular matter.
Okay, so the mass itself is pretty much regular matter. It's not like the dark matter.
I mean, again, there's no way for us to test that directly. Once you're inside the black hole, we don't know what you're made of anymore. But based on what we know about galaxies, that's our best guess.
Okay. And so it appears that we are getting more and more evidence for this supermassive black holes at the center of galaxies. We already have evidence of the stellar size black holes. And there is a gap between these two, right? That is what you call the intermediate
mass black holes.
And what is the sort of the range of that?
So, from a purely observational perspective, the most massive thing we now know at the low end is around 150 solar masses. But I would put that, so I sort of draw the line at 100, because roughly speaking, we know how to make a 100 solar mass black hole in the death of a massive star. We don't know how to make a 150 solar mass black hole through the death of a massive star. So I'd say intermediate mass black holes start at 100 and go basically up to a fuzzy upper boundary that's maybe 10,000 or 100,000. We have some evidence for 100,000 solar mass black holes that live at the centers of galaxies. So that's only a little less massive than the one in our own Milky Way. So that's a pretty large gap.
Pretty large gap. And the puzzle is that we haven't found too many
I wouldn't
those,
say that it's
right?
puzzling in the sense that they're very hard to find. The reason, I mean, everyone just wants to know, I mean, we're interested just whether they exist, of course. But the reason I'm interested in them really relates to this seed question, because we're pretty confident that 10,000, 100,000 million solar mass black holes did not form at that mass. They had to have formed at a lower mass and grown upward. So we think there have to be relics of that process that we should be able to find today. And we hope that the distribution of masses that we find, also where we find these intermediate mass black holes, will provide us clues as to which of those seed channels that we discussed is the most prevalent way that supermassive black holes are made. So I very much expect that they must be there. I think the question is, how do we find them? Because they're so such low mass compared to the supermassive ones that a lot of the signatures we're used to looking for are subtle to impossible to find.
Right. So one direction, I guess, is looking at the smaller galaxies, like dwarf galaxies.
Exactly. So as we already discussed, there are these correlations between the mass of the galaxy and the mass of the central black hole. But the most natural and easiest place to look for low mass black holes is in the centers of low mass galaxies. It's also true that low mass galaxies kind of have more quiescent lives. They tend to eat fewer other galaxies. They just are more boring in some ways. And so there is a theoretical hope, that the black holes that we find at the center of these low mass galaxies may be more indicative of those seeds. Whereas if you look at M87, for instance, the one where we've made a picture of it, that galaxy's eaten so many galaxies over its lifetime that to trace back the feeding history of its black hole is just impossible, right? So that's kind of the motivation for looking at the dwarf galaxies.
And we have a few of those dwarf galaxies around Milky Way. Right?
Yes. The Milky Way has many dwarf galaxies that live around it. And in fact, one of the more embarrassing questions that I'm often asked is, so the most massive friend of the Milky Way is called the Large Magellanic Cloud. And to this day, as I sit and talk to you, we do not know whether there's a massive black hole at the center of the Large Magellanic Cloud, even though it's one of the very nearest galaxies to our own.
Right. Yeah. So is there anything in the theory, Jenny, that makes this intermediate variety sort of unstable? No. So I guess the reason we haven't found them, one is they're difficult to find, and the other is other reason that they sort of swept into the bigger ones over time.
Some of them grew into the bigger ones for sure. How many are left over, like I said, I think would be a clue to how they were formed. But I guess I would say the other reason we haven't found them, aside from the fact that their signatures are very subtle, the other reason we haven't found them is that we really don't quite know where to look. So we talked about looking at the centers of dwarf galaxies in analogy with looking at the center of the Milky Way. But it's quite likely, as you were alluding to, that many of these intermediate mass black holes don't find their way to the center of a galaxy. Maybe they're still living in their globular cluster. Maybe they're floating in the halo of a bigger galaxy.
Yeah, there was some idea that Planet 9 is actually a black hole.
Yeah, that would be smaller than any of the black holes.
That'll be really small. But if you find it, I guess, technological challenges, but you could actually get free energy.
If you say so. I don't know how you're going to convince yourself it's a black hole.
Yeah. So, there are a lot of, I know that you don't do a lot of research in this area, but how they actually die, Hawking radiation. You want to talk just a little bit about what we know today as to what the ultimate state might be for a black hole?
I don't think I have very much intelligent to say about that.
Yeah. Okay. Yeah, I mean, from the little I know is that we believe they would ultimately evaporate, right?
Long period of time. Yeah.
Okay. And so, in conclusion, then, Jenny, what do you think would be the state of the art, just to project forward 5 years, based on all the research that you have done and what you're doing today, in terms of our better understanding of black holes? say 5 years from now? What are the areas that, let me ask you this way, what are the areas that excite you most?
Well,
in
if you'll
terms of
give me
further
15
research?
years, I can tell you what's really exciting.
Okay, 15.
So the very
Yeah.
first thing that's coming is the Vera Rubin Observatory, which will be doing a large time domain survey. So that means looking at the same part of the sky every 3 days over most of the sky. And why that's exciting, and particularly for this intermediate mass black hole question, is that one of the ways we can find black holes that otherwise are invisible to us is if a star passes too close to the black hole and gets ripped apart. That's called a tidal disruption event. And this can light up black holes that otherwise are dormant, and may be a very good way to find these black holes that may be wandering around in their cluster, and we just have no other way of finding them. So I'm very excited about that prospect. I think that's going to open up a new window. The second window, we've talked about these dynamical methods of looking at the motions of stars. What limits you there is just the smallest spatial scale you can see, because you have to see stars whose gravity is influenced only by the black hole. And for very low mass black holes, that is currently impossible with present day telescopes. But if we build 30-meter telescopes, or when we build 30-meter telescopes, they will be able to find the dynamical signatures of 10 to 100,000 solar mass black holes in galaxies out to the Virgo cluster. So a much, much larger part of the universe than we can survey now. So we will really understand the distribution of black holes down to at least 10,000 suns from extremely large telescopes, 30-meter telescopes. So that's item 2. And item 3 is gravitational wave detectors in space, in particular an experiment called LISA, which will have as its sweet spot the mergers of 10, 100, and a million, up to a million, or up to 10 million sun black holes. And then we will be able, and it will be able to see these black hole mergers all the way to the very early universe. So we will see the seed black holes merging, and the signature of the different seeding method should be imprinted on those early merger histories. So the combination of those three, the time domain with the Vera Rubin, the high spatial resolution with the 30-meter telescopes, and the gravitational waves for those intermediate mass black holes, that's what I'm most excited about.
Yeah, so is there anything sort of constraining LIGO? So LIGO can only pick up
frequency.
Certain,
that's right.
I don't know what the right term would be, frequency.
Yeah.
Okay, so that means that it can only pick up
that's right.
size.
That's right. It's not sensitive. So I think next generation LIGO will probably see the merger of 200 to 300 solar mass black holes. And that's really pushing things.
Yeah, and LISA,
right.
You said it's in space. So this is another. So when is
35
that supposed to be launched?
That's why I needed 15 years.
Oh wow. Okay. Yeah. And so that's a totally different technology.
It's still an interferometer. It's still looking at the distance between the different arms, and they've actually flown successfully a technology test mission.
Okay. So will it also be then able to pick up, there is the inflationary hypothesis that, there's gravitational waves coming from inflation.
There are a number of cosmological implications of LISA, and certainly the overlap of LIGO and LISA that I'm not an expert in, but certainly people I work with think about. So yes, in general, the answer is yes, but in detail, I can't speak to it intelligently.
Excellent. Yeah. This has been great, Jenny.
Awesome.
Thanks
Thank
so much for
you.
spending time with me.
Thank you so
And
much. You
good
have a
luck with
great
this
evening.
research. Yeah.
Bye.
You too. Bye. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.